Hi, so for this video, we're going to talk about Chapter 4, Chemical Reactions and Chemical Quantities. Before we get started, you're going to want to have a printout of the periodic table and a printout of the notes that go along with this video. Once you have those, we can get started. Okay, so chemical equations are a shorthand way for chemists to describe a chemical reaction. It gives a lot of information. It gives us the formulas of the reactants as well as the products, the states of matter for the reactants and products, and the numbers of quantities of how they relate to each other. So how many moles of a reactant, and that's going to yield how many moles of product. So we can use this to determine how much reactant we need and then how much product we're going to form. The general form for a chemical equation is what you see in bold there in the middle of the slide. The reactants are going to be always placed to the left. The products are always placed to the right. The yield arrow acts as an equal sign in a math problem. We use the arrow, it's pronounced yield, and it's just telling us from the beginning to the end of the experiment. It's just being that middle placeholder. So there are lots of symbols that we use in a chemical equation to give us even more information, but to continue that shorthand style. And so if we look at this slide, we're shown the abbreviations to represent the different states of matter. And these are written after every formula, whether it's a reactant or a product. And it's pretty intuitive, okay? So we use a lowercase g for gas, a lowercase l for a liquid, lowercase s for solid, and then the unique one here that's used in just a certain circumstance is the AQ. AQ is an abbreviation for aqueous. An aqueous solution is one in which something is dissolved in water. Since water is called the universal solvent, it's virtually 100% used in dissolving most things. We instead of saying plus water in a reaction, we use the AQ to represent a formula that has been dissolved in water. And then we see a reminder of our diatomic elements. It's so important that you recognize these in a chemical equation, because if you're writing the formulas, you need to write the diatomics when they're there, or else you're not going to get the correct numbers that you're looking for down the road. The physical state of matter for each of these diatomics is also listed on the far right. And so that's a handy chart to reference when you're writing these symbols. Here are some other symbols that we use in chemical equations and what their uses are for. The plus sign is used to separate different chemicals from each other. We've already discussed the yield arrow. We've already discussed the states of matter. But then we come to an arrow that's double-sided. The double-headed arrow represents a certain condition where the reaction can go in both directions. And what that looks like is we have a reaction going to make products, then those products, for whatever their reasoning is with the bonding or the environment that they're in, they can decompose and reform your original reactants. So in that case, we say that's an equilibrium equation, and we use the double-headed arrow to represent those. A abbreviation of NR stands for no reaction, and we'll see that a little later on when that's used. The Greek letter delta, that triangle, represents heat being added to a reaction. And then we have a catalyst, and this can take a few different forms. Again, we see the Greek letter delta representing heat. We have the Greek letter lambda that we use to represent light. That's usually UV light when it's exposed to a reaction. And then we have different catalysts that are substances. These can be elements or compounds. And what we would do is we would write the formula for that substance above the yield arrow. You'll recall from biology that a definition of a catalyst is something that makes the reaction occur faster, but it does not actively take place in the reaction. Its formula is not being consumed in that reaction. So it's kind of working in the background in that sense. And so we're going to include its formula above the yield arrow to show that it's not being actively used in the reaction itself. Next, we come to indications of a chemical reaction. And so there are several ways we can tell if what we're observing is an actual chemical reaction, or is it just a mixture that we have of a few substances. So the first one we're going to talk about is when a gas is released. We have an example here with this animating image, and it has a caption underneath. In this image, we see zinc, which is a solid metal, being added to hydrochloric acid. This is a clear liquid. But when they react, we see hydrogen gas being formed. And then what will remain would be a solid zinc chloride. So looking at the reactant states of matter before, zinc is a solid, hydrochloric acid is a liquid. When we mix them together, we get another state of matter, a gas. That gas was not there prior, so that is an indication of a new substance that was formed that is in the gas state. A second indication of a chemical reaction is color change. And so here we see two examples that we can notice in the lab for a color change. The first one is when we mix two different liquids. And so if we mix these two liquids, you can see that originally one is yellow and one is clear, but when they are combined, we have an orange-red appear. That's a new color that was not present in the reactants, so that's an example of a color change. A second example is on the bottom, and in this case, we have a solid that's in the form of a wire that we're going to add to a clear liquid. The wire ends up dissolving and becoming part of a new solution that we see has the characteristic of a blue color. So that is an example of another type of color change. And when I talk about color change and the indications of a chemical reaction, I also like to add an instance that would not be representative of a chemical reaction. And so for this, I like to use the example of making Kool-Aid. You know, those little packs with the powder in them, you add water to it, maybe you add sugar, and then you get a refreshing drink. Well, let's imagine that we're going to make some Kool-Aid. For the sake of our image, let's say it's fruit punch. So it's a red packet. The powder inside is a light red color. You mix it with water according to the package directions, and you're going to get an average red shade of your beverage. Now, what if someone else made the Kool-Aid with the same packet but added too much water? What would that solution look like then? Well, you would predict that it would be a lighter color because it is more dilute. This is not an indication of a color change. In this case, it's the same color, but just a different shade variation of that color. That's not a change. So you want to be careful when observing chemical reactions and noting that the color change is the reason for you saying it's a chemical reaction. A third is the formation of a precipitate. A precipitate is the term used for a solid that's formed when two liquids are mixed. And these are usually aqueous solutions, and so that means that they were a solid substance that was mixed with water to make a solution. And so if we have two different substances that are aqueous, and we combine them together and see a solid form from that combination, you've just made a solid. That's a new state of matter that was not present in the reactants. So that's an indication of a chemical reaction. We abbreviate that substance as PPT period. And so we would usually write that, this would be a product that forms, we would write it after the chemical formula of that product. And so in this example, we see a clear glass container that already has a clear liquid in it. And if you look real closely to the center of this image and at the top, you'll see that another clear liquid is being poured into our container. So we have two clear liquids, and the result of them combining is a yellowish, powdery solid. So here is our indication of a chemical reaction. And you can read the caption there to see what was mixed in this example. Okay, a fourth indication is if heat and or light is observed. So heat and light are two different forms of energy. So the example that you're seeing in this image is a sodium peroxide, which is a yellow powder. Can't really tell from the start of the image that it's in there. Okay, but we imagine a yellow powder mixed with zinc powder, which is gray. So imagine a combination, a mixture of like salt and pepper together, only the salt is yellow. That's what this would look like initially. When we see water being squirted in from the left side of the image, right upon contact, this mixture ignites and a reaction occurs. Water can be thought of as a catalyst in this reaction because it allowed the two solid chemicals to get to a state of matter and arrange the ions so that they're able to contact and make new substances. But we see the bright flash of light and we see the fire that would indicate heat. So we see both in this example of a release of energy. Another example with heat would be if we had a reaction in a test tube and you're holding this test tube and it starts to feel warm, where initially that test tube just felt like room temperature. So the fact that it got warmer is an indication of chemical bonds being broken, and so a chemical reaction is taking place. Another example with heat would be if we're holding a test tube, we add a substance, a chemical reaction occurs where that test tube starts to feel very cold. Chemical reactions can absorb energy to take place as well as give it off. And so if the test tube feels cold to you, that's because the reaction is absorbing your body heat from holding that test tube. So there's a couple examples using heat. So next we're going to talk about the different types of chemical reactions, and there's 5 main ones. The first one we're going to talk about is combustion. This is the fire reaction. And so whenever we have a combustion reaction, the characteristics of it are that we have a oxygen combining with any hydrocarbon, and that's going to always form water and carbon dioxide. So that's why I showed the two products there in red type to show that this is a reaction we can predict pretty easily by knowing that combustions always have these two products. We see two different forms of examples down at the bottom of this slide. The top one says general form. So this is just a very basic, stripped down, minimal look to what these equations look like for you to be able to recognize it's a combustion reaction. What you want to notice is you'll have some substance that is a hydrocarbon. And we learned in the last chapter a few different examples of hydrocarbon formulas. So you know that they can be any number of carbons to hydrogen. So that's why we see just X's in those spots. We always have oxygen being added to it. Oxygen is diatomic, so that will not change. And then we see the formulas for carbon dioxide and water on the product side. A specific example is underneath. In this case, we have a unique looking hydrocarbon that has oxygen tagged onto that formula. Okay. This is the formula for glucose. So maybe you saw that in a biology class. So even though it's not just carbon and hydrogen, glucose reacts the same way when it's being metabolized in our body. So glucose is the result of ingesting carbohydrates, mainly table sugar. And so we convert table sugar, which is sucrose, into this form you see on the screen, glucose. The oxygen that we breathe in is used in part for the metabolism of glucose. We see that carbon dioxide is one of the products. You're breathing that out. And then the water just goes wherever the body needs it. This reaction also produces heat. We don't spontaneously combust, but our body temperature is a direct result of this metabolism. Okay, another example is, is synthesis, and that's also called combination. You'll hear me refer to this type as synthesis. When we have a synthesis reaction, we recognize it by seeing two or more simple compounds or even just singular elements combining to just make one product. So the way to recognize synthesis is that you're always going to have just one formula as your product. For the image here on this screen, I'm referencing one of our labs where we had the magnesium ribbon, heated it up in the presence of oxygen, and we made magnesium oxide. We see a general formula here on this slide as well. So just a very basic looking representation of this reaction. And then we see a more specific example underneath it. When you see that specific example, you'll note that there are 3 reactants there. So the number of reactants don't matter. It's the fact that they all combined to make one product formula that indicates this is synthesis. Next, we have decomposition. A decomposition reaction can be thought of as the opposite of a synthesis. So with decomposition, we're starting with only one product formula. One reactant formula. We start with one reactant formula, and that substance breaks apart into different components. So we can look at the general formula down here and see it's represented by a substance AB that's bonded together, and then after the yield arrow, we see that it's been separated. A specific example is the breaking apart of water. Now, what should be included here is our catalyst above the yield arrow. In the case of breaking water apart, we would use the Greek letter lambda or a symbol of an electron, a lowercase e with a negative sign, to show that we need to provide electricity to break water apart. Water wants to stay together. It's pretty stable. And so to break it apart, we use a system called electrolysis. This is basically the reason for the warning on your toaster not to take a bath while making toast. Next, we come to single replacement. And I nicknamed this one the prom dance reaction. And by looking at the cartoon that I've included, perhaps you can see where I'm getting that name from. Let's take a look at how to recognize a single replacement reaction. Also, I want to note, these are sometimes called single displacement. So you might see that in different texts or videos that you might come across. I use single replacement when I talk about this one. So here we see one element by itself, and it's going to react with a compound. We see the element can either be a cation or anion, and it's going to replace the same charged substance that makes up the compound. So let's look at the specific example on the bottom here to kind of work on what I've just mentioned. We have zinc. Zinc is a metal, so we know that it forms a positive charge. Metals are always cations. Then we look at the formula HCl. H, even though it's not a metal, it behaves like one in a chemical reaction. Hydrogen being in group 1A always forms a +1 charge. So it can be thought of as, like zinc, a cation. So for this reaction to take place, the only possibility that can occur is if the two cations switch places. So the zinc will take the place of hydrogen and bond with chlorine, and then hydrogen is left by itself. You want to note that when the hydrogen is by itself, it has to be written like a diatomic. Okay? And also, when we form our new substance, the zinc chloride, we're forming a new formula, we have to crisscross the charges. And so we would have to be told ahead of time what the charge of zinc is. Here it would have to be a +2. So looking at the picture, what you see is just a cartoon of a couple dancing and a gentleman wearing a peach shirt. The guy with the peach shirt then is dancing with the girl of the original couple, and the original guy in that couple is now by himself. So that's where I get the prom dance kind of cut in image for this reaction. The last one that we're going to talk about is double replacement. This is also called double displacement in other media. So here we have two compounds that are reacting, and they're going to switch partners. So I like to nickname this one the square dance reaction. If you're familiar with square dancing, you could see the cartoon there right underneath, where we have two couples that are dancing, and the letters on their t-shirts just help you keep track of where they are. So we have A and B together, and C and D together to start. After the reaction, we can see that A is now dancing with D, and C is now dancing with B. The boy and the girl in this cartoon is just to represent that a cation and an anion are opposite charges. So the only possibility would be to rearrange these two couples in the way that you see on the screen. We cannot have two anions come together. They would repel, being the same charge. We can't have two cations come together for the same reason. So with these, although it looks complicated, there's only one possibility for a product. And so you can look at the general formula and see how there are two arrows showing the double swap. And then if we look at the specific example, we can get a better picture. So again, you want to note which substance in each compound is the cation. A clue is that they're always written first in the formula. So we have lead and we have potassium. They're going to switch places and be connected to the opposite anions. So the lead is going to connect to the iodine, and the potassium is going to connect to that polyatomic nitrate anion. Whenever you rewrite a formula, you have to redo the charges and the crisscross. Okay? We see here that the nitrate is in parentheses and there's a 2 after it. The reason for that is the crisscross. So this tells me, if we reverse it, that the lead here must have been a +2 charge to form this 2 down here. If we didn't have parentheses around our nitrate, that 2 would be right next to the 3 of the nitrate formula, and it would appear as though we have 32 oxygen atoms, which is impossible. So the parentheses are necessary with the polyatomic to show with that crisscross that you have 2 of the NO3s. When we come to the product side, we have potassium now bonded to nitrate. Well, in this case, potassium is a +1 charge. So when I crisscross it, the nitrate's -1 charge, we don't write ones when they crisscross, right? It's just understood with the symbol being there. So that's why there's no parentheses here. It would just make it look a little more cluttered. So to keep the formula looking cleaner, we don't use parentheses if there's only one of that polyatomic. And so that's why there's no parentheses here. Okay, so let's refer to our note packet that goes along with the video and look at example 1. Okay, so I'm doing the video slightly different format here, and I see that it's already showing the answers. Mental note made. So when we're looking at these, we want to be able to recognize each formula as a type of reaction. So looking at the practice example A, we see 2 elements that are separated and only one product. That's characteristic of synthesis. Next, in example B, we see we have an element and then a compound. We notice from looking at the reactant side and comparing it to the product that lithium came in and kicked hydrogen out of this hydroxide anion. But wait, where was that over here on the reactant side? So I'm going to give you a trick to help you with that, and that's looking at this water. When you write water in a chemical reaction, it might be helpful to rewrite it. Just jot it down on here. Okay, and so it might be helpful to write water as you see here in my drawing. Write it as a hydrogen and a hydroxide ion, and I just put the bond between them there. And so that means when water breaks apart in a reaction, it's going to break apart as the hydroxide ion staying together and then the hydrogen ion being separate from it. And so if you look at water this way in a reaction, you'll see that the Li bonded with the hydroxide anion part of the water molecule. That's a negative charge. Lithium being a metal is a positive charge, so those two would have to come together to make a compound. Hydrogen over here is the hydrogen cation from the water molecule. But because it's now separated by itself, it has to have the two there. Hydrogen is always diatomic when it's by itself. Next, we see one formula for this sodium nitrate molecule. We see that on the product side, it's broken apart. Some oxygen is left. Now, again, the numbers are not going to match up yet. That's coming, right? So if you're looking at the NO3 becoming NO2, but then I have two oxygens here, we'll fix that in a minute. Again, oxygen is a diatomic like hydrogen was. So when it's by itself, you have to show the two there for it being diatomic. So that's decomp. And then the last one, we have a chemical with C's and H's. We have a lot of oxygen being added. And on the product side, we see formulas for carbon dioxide and water. That is always characteristic of combustion. So next we're going to talk about chemical activity. And this is going to pertain to the single replacement reactions. So the ability of an element to react is referred to its activity or reactivity. The more easily an element reacts with other things, the greater its activity is. And so to demonstrate that, we have a couple pictures here. We're seeing some lithium being added to a beaker of water, and a very violent looking reaction takes place. But then we have the lower picture, a gold ring, it looks like, tied to a string, being placed in some water, and there's no reaction there. So lithium would have a higher activity than gold. There's a whole chart that allows us to compare elements to each other to see which one would be the greater activity level. And this is used to predict if a single replacement reaction will occur or if it's not possible. Now I have the chemical Avengers there. We have aramecium being Captain America, thorium, Thor, uranium along with hydrogen forming the Hulk, and then iron forming Iron Man. And so I did this to represent my nickname for the activity series in that it's kind of a popularity chart. And so the Avengers are a popular movie series. And it's kind of where I was going with that. So we get this information from an experiment. We look at all the elements and how they react to each other, and this is what we came up with. Okay, I want to note that here you're always given these two activity series tables. You do not have to memorize these. These are references just like the periodic table is. So first on the left, we see the activity series of metals. The higher up a metal is on the list, the more active it is. If one metal is higher up than a different metal, that means that higher metal can replace the lower one in a chemical reaction. On the bottom right corner, there's a smaller table, and that's for the halogens. We can have one halogen replace another halogen that's in a compound, and the reactivity of them is listed in the same way. Fluorine being at the top of this chart says that it's the most active of all the halogens. So fluorine can replace any of the other anions in a chemical reaction. Conversely to that, the iodine is at the bottom of this list. So iodine cannot replace another anion that's in a chemical reaction. And so let's take a look at an example where we see this. Again, trying something different here. You're seeing the answers here ahead of time, but we're going to walk through how we got them. Okay, so we're going to predict whether or not a reaction can occur by looking at all of these examples of single replacements. Let's look at A. We have nickel being added to lead nitrate. Nickel is a metal and lead is a metal. So the question becomes, can nickel replace lead in a chemical reaction? Let's go back to the activity series and find each of those. So nickel is right here in the middle, Ni, and then a couple down we see Pb for lead. So because nickel is above lead in the activity series, it's more active. It can replace lead, and we see a reaction take place where those two cations switched. The next one, we have magnesium chloride and zinc. And so you can see the end of the story already. Let's go past that. And the question becomes, can zinc replace magnesium? Those are the two metals. So we go back to our chart. We find zinc and magnesium. So I have magnesium right here in the second series of the chart. And then zinc's beneath magnesium here, a few down. So the question is, can zinc replace magnesium? And the answer is no, because it's lower than magnesium on the chart. Magnesium's more active, it's going to stay connected to that chlorine. And so here's where we would use the NR that I referenced at the very beginning with all the symbols. This would be no reaction. Next we have the halogens here, and we're using that chart. So we have bromine by itself, and then a chemical potassium iodide. So because our element that's by itself here is bromine, a halogen, we're going to look and see where's the other halogen to see if it can replace it. And so that other halogen here is the iodine. So we're looking to see, will bromine replace iodine? Going back to the chart, again, we're looking at the halogen chart, we find bromine is just above iodine. So it is more active. Bromine will take the place of iodine, and we have a reaction take place. For the last one, we're going back to metals. We have copper by itself, and then hydrogen chloride, which is hydrochloric acid. So we look for cations, right? In the hydrochloric acid, the hydrogen is the cation. So our question here for D becomes, will copper replace hydrogen? We'll go back to the series. We're going to look at metals. Okay, we've got to find copper. It's down towards the bottom here. And then where's hydrogen? Hydrogen is above copper. So copper cannot replace hydrogen. It's lower. So we have no reaction. Okay, next we're going to go back to look at combustion reactions. We're going to talk about numbers of the different components in a reaction. Okay, we looked at earlier an example where the number of oxygen didn't match on the left side of the reaction to the right. And so we're going to fix that now. Here, our example here is when we have methane in a combustion reaction. So you can see the reaction there. And if we just count how many atoms of oxygen are on the left side of the reaction to the right, we see that they're different. Okay, this cannot occur. What this is saying here is that we had two oxygen atoms and made a third one as a result of this reaction. You cannot create matter. That's the law of conservation of matter, also known as the law of conservation of mass. And so we need to adjust our chemical reaction so that it abides by this law. Okay. If we look at the hydrogen, this is also not possible. We have 4 hydrogen atoms on the left side of the reaction and only 2 on the right. So where did those 2 other hydrogens go? You can't make matter disappear. It has to be accounted for. And so what we have to do in this case is balance this chemical equation. So to balance, we're going to do some certain steps here. We have to be careful. Okay, this image shows the chemical equation as it's balanced. And you'll notice what's different here is that we've added these larger numbers in front of 2 of the formulas, the oxygen on the left and the water on the right. And we have the model representation underneath so that we can also see how the numbers are now balanced. Let's look at all the hydrogens. Over here on the left side of the arrow, I have 4 hydrogen atoms in this molecule. On the right side, I still have 4. They're the white. I have 4 white circles. So the number of hydrogens did not change. They're in different spots, they're connected to different atoms, but that's what a chemical reaction is. The fact that I still have 4 atoms is balanced. When I look at the oxygen, it's diatomic, so we see 2 pairs because of that 2 that's now placed in front of the formula. So there's 4 total oxygen atoms here. If we go to the right, I have 2 oxygen atoms in my carbon dioxide molecule, and then I have 1 oxygen in each of my 2 water molecules. So now this equation is balanced. It abides by the law of conservation of mass. Here we see another example using sulfur and iron. So if we heat this up on a Bunsen burner, we're going to get a new product called iron sulfide. And when we do that, we can take our measurements in grams of the sulfur and the iron, and you see those measurements right here, 32 and 56 grams. When we heat them up and make this new compound, iron sulfide, we can mass that once it's cooled and see that it's 88 grams. Well, here we have the law of conservation of mass being met, because if we go back and add up 32 plus 56, that comes out to 88. And so the law of conservation of mass was abided by. So before we get into balancing some more examples, we're going to see how this process would play out on some examples like the homework. So in example 3, we're tasked with writing an equation from a sentence. So let's read this. Write the equation for the formation of sodium hydroxide and hydrogen. I'm going to stop there because I got a verb there, formation. That tells me what I'm about to read after the word formation are going to be products. So sodium hydroxide and hydrogen are the 2 products. Let's read more. From the reaction of, we have another verb now, okay? And so the reaction of sodium with water, the way that's phrased tells me that sodium and water are my reactants. So you've got to look for those clue words to tell you what substances are going to be on the left side of the arrow and which are going to be on the right. So we're going to first write out just the words, the names of these substances for this reaction, and place them on the right sides, the correct sides of the arrow. Then we're going to make our formulas. Whenever you write a formula, you need to look at the charges and crisscross them. So sodium hydroxide, we have the hydroxide polyatomic ion, that's a -1 charge. Sodium being in group 1A, +1 charge. Okay, they're both 1s. We don't need to write anything. Okay, you know the formula for water, and the other 2 are just single elements. Sodium is an atomic element, whereas hydrogen is a molecular element. You have to recognize these diatomics. I've stressed that several times because if you don't get this step correct, the rest of it's going to be wrong. So make sure you spot those. All right. Next, what we're going to do is we're going to place a little line in front of each formula in the whole reaction. Okay, this is to represent a place where we can put a coefficient. So just like in algebra, when we have a coefficient like 2 in front of x, it's going to represent how many of that substance we have. So 2x means I have 2 x's. Okay, we're going to place numbers in front of each of these formulas here to balance our number of atoms. You cannot change the subscripts to make it fit and balance it. You're changing what that substance's identity is if you change the subscripts. So you can't do that. What you have to do is just change how many of them you have, and that's the coefficient. So when I do these, this is how I set it up. I look for the yield arrow, and then I draw a vertical line straight down. That's separating the reactant from the product side of the equation. Then what I do is I look at the reactant side and I read left to right, and as I come up with a new element formula, I write its symbol underneath here in this way. This is going to become my current record of numbers of atoms as I try to balance this equation. So it's always going to change down here. Now I said I read left to right. I just do that for the reactant side and write my elements in that order. And then when I'm done with the elements on the reactant side, I take that column that I just wrote of formulas and I just write it the exact same way on the product side. The elements might be in a different order over here on the product side, and so I just copy what I had on the reactant side here so that I can easily look left to right and compare sodium to sodium, oxygen to oxygen, and I'm not looking around for a different order of these numbers. Okay, so that's why I do that. And then we're going to get an initial count of what we have for each element on each side. So again, I would start left to right again. I would look at the sodium here and say I have 1 sodium on the left. So I'd put a 1 next to the sodium. Then I'd look to the right side and I'd say, oh, I only have 1 sodium on this side too. Put a 1 next to the sodium on this side, and they're the same number, so sodium doesn't need to be changed. It's balanced. I then would look to the next element. Next we have hydrogen. Here we have water, so there are 2 hydrogens on the left side. I'd put a 2 next to the H. Then I'd go to the other side of the equation, and here's where it gets tricky. We're looking for the total atoms of each element on the entire side of the reaction. Hydrogen is in 2 different chemicals here on the product side. We have a hydrogen here in our sodium hydroxide, and then we have 2 more hydrogens by themselves over here in our second product. So total, I have 3 hydrogen atoms on the right and only 2 on the left. Hydrogen is not balanced, so I need to balance this entire equation. So to try to fix that, I can put a 2 coefficient in front of the entire formula where there's only 1 hydrogen. I chose to do this because there's only 1 hydrogen in this formula. It's going to be very difficult to near impossible to try to match an odd number on the other side of the equation, especially since I'm starting out with an even number of 2 on the left. It's not going to happen. So I have to make the right side an even number as well. So when I do a new count of my hydrogens, this 2 coefficient is going to distribute, to use another math term, to every element that's in that formula. Okay? If you hit the plus sign, you stop distributing. That's the end of that formula. So the 2 will go to the sodium, the 2 will go to the oxygen, and that 2 will go to the hydrogen of the sodium hydroxide formula. The hydrogen over here is not affected, but we need to include it in our recount of hydrogen on the product side. So now our total of hydrogen on the product side is 4. So I have a 4 now down here next to the symbol for hydrogen. Okay, and so now I have 4 hydrogen on the right, but I only had 2 on the left. So hydrogen is still not balanced. But if I put a 2 in front of this water, that would then distribute and multiply and make 4 hydrogen on this side. 2 times 2 is 4, so I have 4 hydrogen now on the left as well. I balanced the hydrogen. But wait, I'm not done. A lot of times when you balance one element, you unbalance others. And that's what we did in this case. That 2 that we put over here first went to the sodium, oxygen, and hydrogen. So now I have 2 sodiums here and only 1 on the left. I've got to fix that. So by adding a 2 coefficient in front of the sodium on the reactant side, I now have 2 there, and I have 2 oxygen from this 2 in front of the water distributing to the oxygen here, and I have 2 oxygen on the right from this 2 coefficient distributing to the oxygen of the sodium hydroxide. So looking at our chart at the bottom, we can read left to right, sodium 2, that's balanced. Hydrogen 4, that's balanced. And then oxygen 2 on the other side. This is now a balanced equation. And so this is just kind of a recap. I got a little ahead of myself. I wanted to highlight where the 4 comes from again. So it's by multiplication with the subscript. Here are some helpful hints. And I want to preface this by saying balancing is really difficult when you first start it. Okay, so these are some hints to help you. Many times you'll find yourself trying to balance an equation and you get very frustrated because it never works out. When that happens, you want to take a step back and focus on something else for a few minutes. Watch some TV, call a friend, text someone, do something completely different to clear your mind and go back to it later. Okay. Here are some hints, though, when you're getting started with a new equation to balance. You're only going to balance one element at a time. You saw how we balanced the hydrogen and made sure that that was complete before turning our focus to those sodiums. You don't want to recognize, oh, the sodium's not balanced now because I'm trying to fix hydrogen and that coefficient's going to go to sodium as well, and now you're thinking of 2 different elements at once. You don't want to do that. Make a coefficient, adjust how many atoms change, and then fix one element at a time. The next tip is when you see a polyatomic ion in a reaction, you want to double check that the formula for the polyatomic does not change from the reactant side to the product side. And let's look at the example at the very bottom of the screen to demonstrate this. This looks really complicated, right? There's a lot of large formulas here, but I've highlighted the sulfate polyatomic ion. We could see that on the left side of the equation, SO4 is just by itself there. And then on the product side, I have SO4, still SO4. An example of this not working would be if it was SO4 on the reactant side, but then I only found SO3 on the product side. That's sulfate and sulfite. They're different. I can't do this trick. But in this case, sulfate didn't change, so I could treat it as if the sulfate were a single element when I look to balance the equation. That is something, if you feel comfortable noticing that, you can do this trick and it saves a few steps. Otherwise, you can then always look at it separated. You can look at barium, sulfur, and oxygen as separate elements and still get the right balanced equation. It just might take you a few extra steps. The next one is to look at hydrogen and oxygen last. Try to balance the other reactants or the other elements first. Hydrogen and oxygen tend to be a pain in the butt, and they're always, you go to fix one and another one gets thrown off, that sort of thing. So sometimes if you focus on other elements and balance those first, the hydrogen and oxygen will iron themselves out in the process and be balanced in the end. If they're not, you want to focus on them last. And if you have both hydrogen and oxygen left to balance in an equation, how do you know which one to choose? You want to save the one that's in the most places for last, like if you had oxygen in more than one product formula. The last tip is to use pencil. You're going to be keeping track of the current number of atoms. You're going to be changing coefficients as you see what originally looked like it would work does not. And so to avoid the mess, you're going to need a pencil. Get a pencil. All right, let's look at example 4. Balance the equation from the formation of magnesium nitride from its elements. Okay, so reading the equation, I see the verb formation of, so I know what I'm going to read next will be my product. And that's magnesium nitride. I have to figure out what that formula is using the symbols and the charges. So I look on the periodic table and I find magnesium. I see that it's in group 2A, so magnesium has a +2 charge. I then notice that the name here is nitride. The IDE ending means that it's a single nitrogen that's an anion. It would be polyatomic if this said nitrate, ATE, instead, or nitrite, ITE. But here it has IDE, and that always means a single element, but it's an ion. So you got to look for those clues. So we have our two elements and their charges written here. We're going to crisscross the charges to get our compound formula. And so when we do that, our formula would be Mg3N2. That's our product. Then we know it's saying from its elements, so those are our reactants. And again, nitrogen is a diatomic. We have to spot those, or else this will never balance. So we have to put the subscript 2 for nitrogen's formula. Now we're ready to see how to balance this equation. The formulas have to be written correctly at this step, or else you're not going to balance, and you're going to get really frustrated. And so seeing the 3 magnesium on the right, I can put a 3 in front of magnesium. It's by itself. On the left, it's not going to affect any other element numbers, so that was an easy fix. And that's all I had to do. The 2 nitrogens weren't affected. So take a look at this, conceptual connection 1. So the idea with the conceptual connection problems is that you shouldn't have to do the workout. You should be able to just look at it and think about it. But let's see. How many oxygen atoms are on the right-hand side of the following equation? So just want you to count them. Go ahead and take a look, get a number, and then we'll discuss. All right, did you count them all on the right? Well, we have a 2 coefficient in front of this iron oxide and the subscript of 3 for that oxygen. So there's 6 right there. And then we have the coefficient of 4 in front of the carbon dioxide with our subscript 2 for the oxygen. 4 times 2 would give us 8 here. And we're adding them. There's a plus sign. So 6 plus 8 gives us 14. So there's 14 total oxygens on the right side of this equation. Conceptual connection number 2. Which quantity or quantities must always be the same on both sides of a chemical equation? Is it the number of atoms, the number of molecules, or the number of moles? It is the number of atoms. That's what you're counting when you balance an equation. You're looking at how many atoms for each element and making sure that they're the same on both sides. So where does this bring us? Chemists don't just sit in a lab and balance equations. There has to be some use for it. And the use for that is the term called stoichiometry. So in here we have an example of the formation of carbon dioxide. This is a combustion reaction. We see a hydrocarbon here. This is octane because there are 8 carbons. We have a bunch of oxygen. Combustion is burning. We're going to get CO2 and water out of that reaction. Okay, and so this is already balanced. And look at the numbers here. So when you balance an equation, you want to start with low numbers like 2, 4, right? You start with the even numbers for what I mentioned earlier, but you can see how with the oxygen we had to arrive at 25 for this to end. So balancing can be kind of time consuming, okay? Just a warning. So here we're looking at the relationships of how much reactants I have and how much products I'm going to make. We can think of a chemical equation just like a recipe. It's allowing me to see how much of the reactants I need to have in order to make the amount of products I want. And so we can see for 2 molecules of octane, I can make 16 molecules of carbon dioxide. Okay. Quantities in chemical reactions. The amount of every substance used and made in a chemical reaction is related to the amounts of all the other substances. That's called the law of conservation of mass, and it's also related to why we balance equations by balancing those atoms. The definition of stoichiometry is the study of the numerical relationship between chemical quantities in a chemical reaction. So here's our example again of our octane combustion. The coefficients in front of the formulas are compared to one another, and we can make ratios from them. And so again, think of it as a recipe. For every 2 molecules of octane that react with 25 molecules of oxygen, we're going to get 16 molecules of carbon dioxide and 18 molecules of water. That's our recipe. From there, we can say the following down here at the bottom. And so if you're not familiar from a previous math class, ratios are written in math this way with a colon in between the terms that we're saying are similar to each other. Let's take a break and make my favorite food, pizza. So an example of stoichiometry using something you're familiar with is right here. So let's say that the number of pizzas you can make is dependent on how much of each ingredient you have. And for this example, our pizza has to have 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese. That together will make 1 pizza. Okay, so then we can make the following statement that these are in a ratio to each other. 1 crust per every 5-ounce sauce per every 2 cups of cheese gives us 1 pizza. Okay, so then we can solve problems that arise like how much pizza can we make if we have 10 cups of cheese? Okay, so we're going to set this up just like we would change grams to moles. We're going to start with what's given. 10 cups of cheese is what we have. And we're going to use our ratio that we got and use that as a conversion factor. So we're going to set it up so that the cups of cheese cancel. This is my ratio here. For every 2 cups of cheese was 1 pizza. And you just solve it the same as we did with grams to moles. We're going to multiply the numerator, so 10 times 1, and then divide by the denominator, the 2. And so 10 cups of cheese, I can make 5 pizzas with that. We're just focusing on that one ingredient, the cheese here. So all others not being thought of, we can make 5 pizzas. So with a chemical equation, the coefficients are called mole to mole ratios. The coefficients represent how many moles of each substance are needed in that chemical equation. Now, I know I said molecules before when referring to the coefficients, and so I just want to take a second and clarify that. So the coefficients, when we're looking at a balanced equation, and we're looking at that reaction happening only once, then we would use the term molecules, because that's how many individual molecules we need for this reaction to occur. But you know in the lab, we can't look at single molecules together. We have to group them in clumps. And in chemistry, those clumps are moles. Moles can be translated into grams, which we can measure on a balance. Molecules can't. And so that's the difference. It depends on the scenario. So if we're talking about a reaction that we're going to use as a recipe to actually perform in the lab, then the term used would be moles for each of those coefficients. Okay, I've starred something on this slide, so that would be something to really note. The ratio of the coefficients is going to act as a conversion factor between the amount of moles of the reactants and products. And I can look at two products related to each other, I can look at the reactants related to each other, and I can do what I did with the pizza, look at a reactant and how much product I make in relation to each other. So let's go into an example. We have our octane equation. Suppose we burn 22.0 moles of octane. How many moles of carbon dioxide will form? We can answer this. We know that the ratio is for every 2 moles of octane, there are 16 moles of carbon dioxide. So again, we're going to start with what's given. In this problem, we were given 22.0 moles of octane. Next, we're going to write a conversion factor, which is the stoichiometric mole-to-mole ratio. We want octane to cancel, so it has to be on the bottom. The 2 came from the balanced equation. We want carbon dioxide, so that has to be on top. The 16 came from the balanced equation. And then we just do the math like we've always done. 22 times 16, divide that by 2, and we're going to get 176. So for 22.0 moles of octane, there's going to be 176 moles of carbon dioxide produced. Conceptual connection number 3. Use the balanced equation for the combustion of octane, which is the one we just did, to determine how many moles of water are produced by the combustion of 22 moles of octane. You might have to sketch this one out off to the side to calculate it. Go ahead, pause the video, see what you get, then come back and we'll go over it. Okay, so you had some time to think about this equation. How many moles of oxygen of water are we going to make? Well, if we set this up using our mole-to-mole ratio from the coefficients in the balanced equation, we're going to have 22 moles of octane multiplied by 18 moles of water, and then divided by 2 moles of octane, and we're going to get 198 moles of water produced. So the answer was D. Okay, we can go a step further. We were just doing moles of something to moles of something else. We can make this a larger conversion problem by starting out with grams and ask to go to grams of something else. And so for this, we can't directly go from grams of a substance to grams of another. They're not related that way. They're related by the mole. Those are the balanced equation coefficients. So if we're given grams, we have to convert it to moles before we can change to the other substance. So we have a chart here that you can see at the bottom where it's color-coded by substance. So the blue would be one substance, and then the green is another substance. And this is like a little roadmap to help you stay on track with how to do these. Let's take a look at example 6. If we burn 3.7 times 10 to the 15 grams of octane, how many grams of CO2 will form? We're going to look at our molar masses. We're going to need that. And so we can calculate this off to the side, the molar mass of octane and the molar mass of carbon dioxide. Then we need the ratio of how these two chemicals relate to each other using the coefficients. So we can make a note of that. Next, we're going to start with what's given. So the 3.7 times 10 to the 15 grams of octane. We need to cancel grams of octane. So we're going to use the molar mass down here. The numerator becomes 1 mole. The grams will cancel out. So we've just converted our grams into moles of octane. We're not done. We were asked about grams of carbon dioxide. So we need to change this into carbon dioxide. The way we're going to do that is the mole-to-mole ratio of the balanced equation. So the mole of octane is going to need to cancel. It has to be down here. The 2 came from the balanced equation. We want carbon dioxide. So again, it's going to be moles, and the 16 came from the balanced equation. The moles of octane are going to cancel in this step. Notice I haven't done any math yet. We're just setting it up so the units cancel, and then we do the math at the end. So now we have moles of carbon dioxide. The question asked for this in grams, so we have one last step. We've got to change moles of carbon dioxide into grams, and that's using the molar mass of carbon dioxide. 1 mole of carbon dioxide on the bottom, so it cancels, and then we have the molar mass, calculated as 44.01 grams carbon dioxide. Now we can do the math. Multiply all the numerators, multiply all the denominators, do that division, and you're going to get 1.1 times 10 to the 16 grams of CO2. Conceptual connection number 4. Under certain conditions, sodium reacts with oxygen to form sodium oxide according to the reaction. And you see that it's already balanced. Which of the following images best represents the amount of sodium required to completely react with all of the oxygen in the above diagram, according to that equation? And so what this means is you can see the red oxygen molecules that I have above the chemical equation. So we have our chemical equation that's balanced, and then I'm giving you a situation where we have 3 molecules of oxygen. So imagine we're starting with 3 molecules of oxygen, and I'm asking you how much sodium we need using this relationship for ratios here. Then you're going to get that number and then match it to the count for either A, B, C, or D. Take a second, think about it, then come back to the video and we'll see how you did. Okay, so the answer for this equation would be C. Because sodium already has a coefficient of 4, that's for every 1 molecule of oxygen. If I have 3 molecules of oxygen, I'd have to multiply my sodium by 3, and 4 times 3 is 12. Next, we have 3 new terms. We have limiting reactant, theoretical yield, and percent yield. Again, this is where our balanced equations and our using of a mole to mole ratio is used in real life in a chem lab. So if we go back to the pizza recipe to start, it was 1 crust, 5-ounce tomato sauce, 2 cups of cheese. We'll make ourselves a pizza. If we have 4 crusts, 10 cups of cheese, 15 ounces of tomato sauce, how many pizzas can we make? So unlike the example we saw earlier, we're given starting amounts of several of the reactants here. So in order to figure out which one is going to make the most pizzas, we have to do 3 conversions, 1 for each of these reactants. So if we look at the crusts, we're given 4. For every 1, we make 1 pizza. So for the 4 crusts we have, we'll make 4 pizzas from that. Then we're going to go to the cheese. In this situation, we were given 10 cups of cheese that we can use. Well, our recipe says that for every 2 cups, we make 1 pizza. So when we use that as a conversion factor, our 10 cups of cheese would make us 5 pizzas. The last one we have to look at is the sauce. We were given 15 ounces of tomato sauce to use. In the equation, every 5 ounces makes 1 pizza. So converting this, 15 ounces of tomato sauce would result in making 3 pizzas. So now we have 3 possibilities here. But we're not just going to make a pizza with just tomato sauce. We need the crust. And I need to have cheese on my pizza. So we need the cheese. So we're going to look at how many pizzas we can make from each of these and see what the smallest number of pizzas is that we can make, the very least amount. And that would be 3, right? Comparing 3 pizzas to 4 to 5. And so we would say that our limiting reactant, the substance that limits the maximum amount of product we can make, is the tomato sauce, because we're going to run out of that first. I have enough to make 4 pizzas with crust. I have enough cheese to make 5 pizzas, but I can only make 3 total pizzas with the amount of sauce I have. So the sauce is limiting how much product I make. Here's just a visual representation of each of the components here. So you can pause the video and take a closer look at that. Okay, theoretical yield. So in theory, how much should you be making? Okay, so again, we can look at the definitions here, and there's space that I've added in the note packet for this, where I already typed out a space for you to write these definitions, figuring that you're going to want to put those, and then giving you that extra space above for anything else that you want to add in the video. So the limiting reactant is also sometimes called the limiting reagent. They mean the same thing. You may see them in different texts and different medias. Okay. The theoretical yield is the maximum amount of product you can make that you calculated. So by my calculations, we should make 3 pizzas, the previous example. The actual yield is what you actually made when you did the experiment or made the pizzas. So it says here, let's assume that while making the pizzas, you burn one, or you dropped one on the floor, or there was something else that was uncontrollable, and you were only able to make 2 pizzas instead of 3. The actual amount of product that you made is the actual yield. We can then determine a grade for ourselves of how well we did making our product by calculating the percent yield. And the formula is down there at the bottom. The percent yield is found by taking your actual yield, dividing it by your theoretical, and then multiplying that by 100%. So we made 2 pizzas. We had enough material to make 3. 2 divided by 3 is 0.67. Multiplying it by 100 gives us a grade of 67%. That's a D+. In a chemical reaction where we have multiple reactants, it's likely that one of those reactants is going to be used up before the other one. When that reactant is used up, the reaction is going to stop because you don't have everything needed. The reactant that limits the amount of product being made, that's the limiting reactant. Again, sometimes you might see limiting reagent for that. That limiting reactant is going to get completely consumed. It's all used up. There's none left. The reactants that are still there, that can't react and form product because you ran out of the other stuff, those are called excess. They're leftovers. You can pause the video and get these definitions if you wanted to write them down. Here's a couple more definitions and the equation for percent yield. So let's go through an example of this. We're looking at the combustion of methane again. Our balanced equation implies that for every 1 molecule of methane, reacting with 2 molecules of oxygen. Well, what if I have 5 molecules of methane and 8 molecules of oxygen? Which one's going to limit the amount of product we make? Whenever you're given 2 amounts of different reactants, you're going to have to do 2 stoichiometric calculations. You have to do that. There's no other way you can figure this out. You have to say, okay, for reactant 1, this amount, how much product? For reactant 2, I'm given this amount, how much product with that? And then you have to compare the 2. So we have to do 2 stoichiometric calculations going from our starting material, the 5-methane, into carbon dioxide. So with 5-methane, I can make 5 carbon dioxide because the ratio is 1:1 in my balanced equation. So then we're going to use the oxygen. We were given 8 oxygen molecules. We're going to go to the mole-to-mole ratio from the balanced equation, which says for every 2 oxygen molecules, I'll make 1 carbon dioxide. And from here, we see that only 4 carbon dioxide molecules can be made. With the methane, we were able to make 5 carbon dioxide. So the lesser of 2 amounts is the 4 we see with the oxygen. So that tells us the 8 oxygen molecules is our limiting reactant. The methane, having 5 molecules of methane, would be our excess reagent. For this conceptual connection, it's a little tricky, so let me clarify something here. We're given a balanced equation of how this reaction takes place. Nitrogen and hydrogen come together and make ammonia. And you can look at the flask there off to the right. Count how many nitrogen and hydrogen molecules are in that flask. That's your certain conditions, your special values to use that you're given with this balanced equation to figure out how much ammonia we'll each make. So I see 2 nitrogen molecules in blue in that flask at the top. So I'm going to start with 2 nitrogen molecules, use the balanced equation, and calculate how much ammonia I will make from that. Then you want to do the same with the amount of hydrogen that you count in that top flask. When you're done, you're going to see how much product are you going to make and pick A, B, or C down at the bottom to represent your answer. In flask A, they just marked what each one looks like so you can recognize them. All right, so the NH3, it has 1 blue and 3 white stuck to it. Pause the video and let's see what you get. All right, so if you were to calculate this for 2 nitrogen molecules and 1, 2, 3, 4, 5, 6, 7, 8 hydrogen molecules, what you'll be left with is what's represented in flask C. You're going to run out of nitrogen first. That's going to limit how much ammonia you make. Oops, sorry, I went too fast there. I thought I was at the end. Not quite. Okay, so when we work in the lab, we measure the reactant quantities in grams. We've been over this, okay? So to find the limiting reactant and theoretical yield, we first have to convert that grams into moles. Remember, the moles are the coefficients in the balanced equation. So we have to change our grams to moles in order to use that balanced equation and compare one substance to another. So here we have example 7. A reactant mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. Then we have our balanced equation. This is what we did in the lab, making magnesium oxide. We're asked with which one of these would be the limiting reactant and what our theoretical yield would be. And so what I like about this is the picture that's included. That shows up top calculating the theoretical yield of magnesium oxide, starting with the 42.5 grams of magnesium up there in blue. You would go that entire distance with that. Then you would do the same calculation on the bottom you see in green there for our 33.8 grams that we're starting with for oxygen. And then you can see the conversion factors needed to go from each step. So this then fills in that chart on the previous slide with all the numbers now. So again, you need to do 2 stoichiometric calculations, one reactant to product and then the other reactant to the product. And in some word problems, it may not specify what product you're trying to calculate for the amount that you want. And so if you have a problem that says that, they want the theoretical yield, but there's carbon dioxide and water on the product side, and they didn't tell you which one to calculate. In that case, you can pick which product you want to form. And so if it says that, just look out for that. This is our last slide. So with example 7, we're going to end this chapter 4 lecture. And so be on the lookout for the accompanying homework assignment to this lesson. Thanks so much.